Next, let us look at quadratic programs, or in short QP, which is written as minimization of half x transpose px plus q transpose x. So this is for x in Rn. So I've written a QP for x in Rn, and we may have some linear constraints of the form gx less than equal to h and ax equal to b. So there are both linear inequality constraints and linear equality constraints. Note that if there are no constraints, so if there are no constraints, the problem is simpler. In fact, we have already seen that problem. So if there are no constraint, then the problem can be written as minimize over x, half of x transpose px plus q transpose x, whose solution can be obtained directly by differentiating the objective function with respect to x. So we can say that gradient of f of x equal to 0 if we call this as f of x. So which would be equivalent to saying that p times x plus q equal to 0. Right? So we have already seen this case. If you have a simple unconstrained quadratic program, then its solution is the solution of this system of equations px plus q equal to 0. So this is a system of equations. But that is not necessarily the case if you have constraints. If you have constraints, then this is not the solution. There is also a related problem, which is that of quadratically constrained quadratic program. So quadratically constrained quadratic program, which as you can guess is simply QP, but instead of linear constraints, we have quadratic constraints. So we write it as minimization of half x transpose p naught x plus q transpose x, and subject to half of x transpose pi x plus qi transpose x plus ri less than equal to 0. So this could be for I equal to 1 to m and ax equal to b. So this is the quadratically constrained quadratic program. Now, as we already know, QP is convex whenever, so this is convex when P is positive semi-definite. This is a convex optimization problem. Whenever P is positive semi-definite, you can guess that because the objective would be a convex function whenever P is positive semi-definite. In the same way, QCQP is convex. So this is convex whenever Pi are positive semi-definite. P0 as well as Pi are all positive semi-definite, then this is a convex. Affine equalities we are already allowing. So QCQP is convex whenever all of these Pi's and P0 are positive semi-definite matrices. So just as an example, let us consider a quadratic program which is not convex and which is unbounded below. So this is just for an example. So it is possible sometimes that you need not always go to the numerical software to solve a problem. Sometimes you can just get the problem solution by just properly analyzing the problem. So let's consider an example, which is that let's say P is equal to minimum over x transpose ax, where A is not necessarily PSD. So it is not positive semi-definite. So what can we say about the solution of this problem? So the claim is that P is equal to minus infinity. Remember our notation? We said that a problem solution is minus infinity if it is unbounded below. So how can we say that this is minus infinity? Since A is not PSD, this must imply that there exists an eigenvalue of A, let's say the minimum eigenvalue of A, which is less than 0. It has to be, because otherwise if the minimum eigenvalue is greater than 0, then the matrix would be positive definite. So there has to be a eigenvalue which is less than 0. So let's say that, let's carry out the eigenvalue decomposition. So this implies that AU is equal to lambda min times U. So here U is the eigenvector. So this is the eigenvector corresponding to the minimum eigenvalue of A. So there must exist a corresponding eigenvector. So let's see what happens if we take an x value which is proportional to u. So here x and u are vectors and alpha is a scalar. So alpha is a scalar. So let's say that if we substitute x equal to alpha times u, then, so in general, it is not necessary that x will be of this form. It is not necessary that x will be alpha times the eigenvector u, which corresponds to the minimum eigenvalue of A. So how can you relate minimum over x, x transpose Ax? So how can you relate it with minimum over x, x transpose Ax, where x is indeed of this form? So let's say we have two problems. In one, I can take any x, and in the other, I can take only x which is along this direction of u. So how do we relate these two problems? Note that in this problem, there is an additional constraint. So what is the impact of such an additional constraint? Whenever you put an extra constraint on an optimization problem, you are minimizing something, you put an extra constraint, that minimum value could get hurt because of that extra constraint, right? So the minimum value may increase. So in other words, I want to say that this is less than equal to this. So whenever you put an extra constraint, the minimum value could increase. Conversely, if you remove a constraint, then there are more options for x to be, and therefore the minimum value could decrease in that case. So whenever I put an extra constraint, the minimum value can increase. So this was P. Let's call this as P2. So what can we say about P2? So let's say P2, and we have already seen that x is of this form. So this P2 will be equal to minimum over alpha. So now basically I can just substitute. I already know u. By the way, u is fixed because it is the eigenvector corresponding to some eigenvalue of A. So this is a minimization only over alpha because u is fixed. So I will get minimum over alpha square times u transpose AU. And what is u transpose AU? Remember that AU was lambda min times u. So this will be equal to alpha square times lambda min times norm square of u. Okay, so this will be equal to alpha square times lambda min times norm square of u. Now, note that this term is greater than equal to 0. Alpha square for whatever alpha I choose is greater than equal to 0, and lambda min is less than equal to 0. In fact, we know that lambda min is strictly less than 0. So overall, this term is less than equal to 0. And if we choose alpha not equal to 0, then it is natural that this term will be strictly less than 0. So what is the minimum of this term over alpha? What alpha should I choose so as to minimize this term? It is clear that I should choose alpha as large as possible, right? So it should be clear that alpha should be chosen as large as possible so as to ensure that the objective function here becomes as small as possible, which means that P2 is minus infinity. So again, P2 is minus infinity because the objective function can be made as small as possible. It can be made minus infinity by choice of sufficiently large alpha. So this is an unbounded below problem. So this problem that we were considering was unbounded below. And therefore, this minimum P is always less than equal to P2. So if P2 is minus infinity, naturally P is also minus infinity. So this implies that P, which is less than equal to P2, which is minus infinity. So this implies that P is also minus infinity. So therefore we have concluded that this problem, when A is not PSD, is unbounded below. So you have to have a positive semi-definite matrix in order to make sure that this has a finite solution. Otherwise, you can always take X in the direction of the negative eigenvector and then scale that to infinity in order to go to minus infinity. So in n-dimensional space, this is a function which goes to minus infinity in certain direction. And we are basically trying to find a way to find that direction. So here we have found a way to find that direction, and that direction is the direction of the eigenvector corresponding to the negative eigenvalues. In fact, if there are more than one negative eigenvalues, we can take any of the eigenvectors corresponding to any of them. So this is just an example, simple example, where a quadratic program is there and it is unbounded below.